Hello everyone, and thank you for joining this session. And my name is Sharath Kumar Bandaru, and I'm an independent researcher with a professional background in cloud connectivity, network infrastructure for fiber optics, and data center engineering. Over the 8 years, I have worked on projects involving in the enterprise's cloud connectivity, optical network optimizations, infrastructure resilience, and mission critical network designs. So today I'm pleasure to present my research titled Resilient Cloud Connectivity, which is a three-layer framework for availability and cost optimization. This topic is becoming increasingly important as organizations continue to accelerate their digital transformation initiatives and migrate critical applications to the cloud environments. As business become more dependent on cloud platforms, ensuring the reliable, resilient, and cost-effective connectivity is no longer optional. It has become a strategic business and resilient requirement. Throughout this presentation, I will discuss the major connectivity challenges organizations for the phase today and introduce a practical framework that can help improve network availability, resilience, operational efficiencies, and cost optimization. So resilience cloud connectivity, a three-layer framework for availability and cost optimization. In today's technology landscape, organizations are operating across multiple cloud providers, so multiple geographic regions and increasingly complex applications architectures. Modern enterprises are no longer running applications from a single data center. Instead, workloads are distributed across the public cloud platforms, private environments, hybrid infrastructures, and edge computing locations. While this transform creates a tremendous opportunities for innovations and scalability, it also introduces new connectivity challenges. Organizations must maintain high availability, low latency, strong resilience, and cost efficiency simultaneously. Unfortunately, achieving all four objectives is often difficult. Many organizations focus heavily on cloud adoption but underestimate the importance of connectivity architecture. But my research proposes a structured three-layer framework designed to address these challenges. The framework consists of physical diversity, intensity control, and operational governance. Each layer addresses a different aspect of resilience, and together they create a comprehensive approach for supporting mission critical cloud workloads. The challenge mission critical workloads demands more from the network. Before discussing the framework itself, it is important to understand why modern enterprises need to be approached for connectivity today's business applications are significantly different from those used even in the decades ago. Organizations now really on distributed applications, microservices, architectures, and cloud native platforms. Artificial intelligence are like workloads, real-time analytic systems, and global collaboration tools. These technologies creates unprecedented demands on network infrastructure. There are four major challenges that organizations must address. The first challenge is availability. Many business critical systems operates around the clock and require continuous connectivity. Even a short interruption can affect customer, employees, and revenue generation operations. Organizations therefore expect extremely high upon a minimal service disruption. The second challenge is latency. Certain applications, particularly those involving the financial transactions, healthcare systems, industrial automation, and real-time collaboration, are highly sensitive to delay. Even same increases in latency can negatively affect user experiences and business performances. The third challenge is resilient. In the past, organizations often relied on a single internet provider of a single connectivity path. Today, that approach is no longer acceptable. A fiber cut, carrier outage, or infrastructure failure can create significant operational disruption. Modern architectures must be designed to withstand failures and continuous operating even when components become unavailable. The fourth challenging is cost efficiency. While organizations need highly resilient connectivity, they must also manage budgets carefully. Bandwidth consumption continues to increase as business adopt cloud services, video collaborator platforms, artificial intelligence applications, and large-scale data processing workloads. As connectivity requirements grow, costs can escalate rapidly if architectures are not designed intelligently. Therefore, these challenges face organization today is not simple how to improve connectivity. The real challenge is how to achieve high availability, low latency, strong resilience, and cost efficiency simultaneously. This is precisely the problem that the three-layer framework presented in the research seek to be addressed. And the next one is from framework overview. Three layers of resilient cloud connectivity. Having discussed the challenges facing modern enterprises, let us now look at the proposed framework. The framework is built around the three interconnected layers that work together in improved cloud connectivity resilience. The first layer is a physical diversity, which focuses on eliminating the infrastructure level single points of failure. The second layer is intelligent control, which ensures the traffic is routed according to the business priorities rather than simply following the static network paths. The third layer is operational governance, which focuses on visibility, monitoring, accountability, and recovery procedures. What makes this framework effective is that each layer addresses a different category of risk. Physically, this diversity will definitely reduces the infrastructure risk. Intelligent control reduces the operational and performance risk. Operational governance reduces the recovery and management risk. Organizations often even focus heavily only on one of these areas. For example, like they may invest in redundant circuits but fail to implement the effective monitoring. Others may deploy advanced routing technologies but neglect physical redundancy. The framework encourages a balanced approach where all three layers support on one another. So together this provides a practical roadmap for building the connectivity architects capable of supporting the modern cloud workloads. And the next one is layer 1, physical diversity. So the first layer of the framework is a physical diversity. This layer will generally form the foundation of resilient connectivity because resilience must begin with the physical infrastructure itself. No matter how advanced software and automation become, they cannot compensate for a complete loss of physical connectivity. Physical diversity means designing the network so that they can continue operating even when interfaces failures occurs. Instead of depending on a single path, a single carrier or a single faculty organizations distributed the risk across the multiple independent components. This includes geographic diversity, carrier diversity, and path diversity. For example, if a business relies entirely on one fiber routing entering a building, single construction accident could server connectivity. However, if multiple independent routes enter from a different locations and are provided by the different carriers, the impact of that can be significantly reduced. The objective is not simply to recover from failures, but to prevent the failures from causing server interruptions in the first place. And the organizations increasingly recognize that cloud resilience start at the physical layer, but building the diversity into infrastructure which creates a foundation upon which all other resilience strategies depends. The next one is eliminating single point of failure. So this is one of the primary objects of physical diversity, which is eliminating the single points of failure. A single point of failure is a component whose failure can cause service disruption across the entire environment. There are three important dimensions to be considered. The first is geographic diversity, and connectivity should be distributed across the multiple physical locations, ideally separated by sufficient distance to avoid the common risks. This may involve like different facilities, campuses, metropolitan areas, or cloud regions. The second dimension is carrier independence. Many organizations mistakenly assume that they have the redundancy because they purchase the services from the multiple providers. However, these providers may share the infrastructure behind the scenes. True carriers independently requires like separate last minute connectivity, and also separate the backbones network and separate the routing domains. The third dimension is a multipath architecture. Instead of maintaining the backup circuits that remain the ideal until a failure occurs, organizations can utilize active designs where multiple paths carry traffic simultaneously. This approach improves resource utilization while reducing the failure times. When these three dimensions are combined, organizations create connectivity architectures which are capable of withstanding infrastructure infrastructure failures without significant operational impact. And the next one, if we are talking on designing for blast radius. So designing for blast radius is when designing resilient architecture, it is useful to think in terms of blast radius. A blast radius refers to the extent of impact caused by a failure event. So examples includes like fiber cut, facility outages, power failures, natural disasters, carrier disruptions, and equipment failures. The goal is to ensure that a single event cannot affect all connectivity paths simultaneously. One important strategy is implementing the diversity entry points into the facilities. So connectivity should be building through the physical separate routes whenever possible. Another strategy involves maintaining independent routing with the domains through the separate autonomous systems and non-overlapping providers with the relationships. So the cloud attachment diversity is equally important, where the organization should distribute the private cloud connections across the multiple edge locations with the availability zones and the regions. This reduces the dependency on a single attachment point. By continuously evaluating the potential blast radius scenarios, organizations can identify the hidden dependencies and that can be obvious from the local networking diagrams, and this proactive approach significantly improves overall resilience and reduces the operational risk. And the next one is the layer 2 intelligent control. So the layer 2 intelligent control is once a resilient foundation has been created and established, the next challenge is managing the traffic intelligently. This brings us the second layer of the framework with the intelligent control. So the modern networks carries a wide variety of traffic types. Some applications are high sensitive to latency and packet loss, while others can tolerate delays without the significant impact. So treating all traffic equally often results in efficient resolutions and the resources with the utilizations and unnecessary cost. So the intelligent control introduces the application awareness into the routing decisions. Instead of routing traffic solely according to the network topology, organizations will route the traffic based on the business priorities and the application requirements and real-time network conditions. So the technologies such as SD-WAN, traffic engineering, quality of services policies, and dynamic path selections, which will enable the organizations to make the smarter decisions about how traffic will flow through the network. So the result is a connectivity in environment that are not only performs better but also aligns more closely with the business objectives. And the other topic is going to be the application aware routing. The core principle behind the intelligent control is simple. Not all traffic has an equal value. So organizations generally should classify the applications according to the business criticality and assign connectivity resource accordingly. So the one includes the mission critical application is example include the financial systems, healthcare platforms, manufacturing controls, and real-time transaction processing. So these applications require in the highest level of availability and performances. So the two include standard business applications such as collaboration tool, enterprises software, and internet protocol systems. These workloads require reliable performances, but generally having slightly lower sensitivity. Tier 3 includes a bulk traffic such as backup, software updates, and large-scale data system transfers. So these workloads can often tolerate high latency and low priority routing. But by matching the traffic classes with appropriate connectivity resources, organizations can improve the efficiency while ensuring that the critical applications will receive the protection they require. And the next one is balancing performing, how it can against the cost. One of the most important aspects of network architecture is balancing the performance against the cost. Every organization operates within the budget constraints, making it essential to allocate the resources strategically. Dedicated the private circuits, which provides the exceptional reliability, predictable latency, and strong service guarantee. However, they also present the highest connectivity cost. So the broadband internet connectivity often significantly lower cost but may introduce a greater variability in performances. SD-WAN solution will help bridges this gap by intelligently selecting the path forward on application requirements and network conditions. And organizations can reserve the premium connectivity for critical application while directing the lower priority traffic over most connectivity effective paths. Traffic shaping and quality of service mechanism further improve efficiency by ensuring that critical workloads can receive like sufficient bandwidth even during the periods of congestion. The ultimate goal is not to maximize spending but to maximize the business value. Intelligent routing allows to the organizations to achieve the resilience and performance without the unnecessary increase in cost. The next one is a layer 3 operational governance. The third and final layer of the framework is operational governance. While physical infrastructure and intelligent routing are important, resilience ultimately depends on how effectively systems are monitored and managed. Operational governance focuses on accountability, visibility, decision making processes, and recovery procedures. Many outages are prolonged not because of technology fails, but because of organizations lacks clear with the ownership and escalation process. But the teams may spend valuable time determining the responsibilities instead of resolving the issues. With effectiveness, governance establishes clear service invoiceships and ownerships, documented recovery procedures, and predefined communication channels too. It ensures the organizations will respond consistently and efficiently during the incidents. This layer transforms resilience from a pure technical objective into an operational capability that supports the long-term business continuity. And the slide 12 is observability across the multiple vendors environments. So modern enterprise environments often span multiple cloud providers, so like a career platforms and technologies, and the complexity which creates a significant monitoring challenges. Observability is the ability to understand the system behavior throughout the comprehensive visibility into infrastructure and application performances. Organizations should collect telemetry across all connectivity layers, including the network flows, routing changes, application performance metrics, and cloud native monitoring data. And BJP monitoring helps detect routing anomaly, flow analytics reveals traffic platforms, synthetic probes help identify degradation before users experiences issues. The objective is to move beyond reactive monitoring towards proactive visibility. Instead of discovering problems after customers are affected, organizations can identify the risk early and take correctivity action before the service even degradation occurs. Strong observability capability significantly reduces mean time to detection and improve overall operational resilience. Next one is a failure domain mapping and runbook. So, failure domain mapping is critical practice for understanding the infrastructure dependencies. A failure domain consists of a components that share common risks. Examples like include shared power systems, shared fiber routes, shared carriers, or shared cloud services. Without proper analysis, organizations may unknowingly introduce like hidden dependencies that undermine resilient objectives. Alongside failure domain mapping, organizations should develop the detailed recovery runbooks, a runbook that provides the documented procedures for handling the specific failure scenarios. Each runbook should define like a detection criteria and escalation paths, recovery actions, validation procedures, and rollbook plans. Equally important is regular testing. Runbooks should be exercised throughout simulations, drills, and failover testing to ensure they remain effective. When failure domain mapping and runbook developments are combined, organizations should significantly improve their ability to recover the disruption. The phased implementation path. Building the resilience is a journey rather than a single project. Most organizations cannot achieve the full connectivity resilience immediate due to the budget, operational, or technical constraints. So, a phased implementation approach allows the organizations to make sure the meaningful progressive while managing the risk. So, the first phase is assessment. The organization should evaluate the existing connectivity architecture and identify the failure domains. The second phase is hardening. This involves like deploying physical diversity, carrier redundancy, and multiple path connectivity. The third phase focuses on optimization throughout the intelligent routing, so traffic classification and policy enforcement. The final phase introduces the governance capabilities such as observability, platforms, recovery procedures, and resilience testing. Each phase delivers the independent value while preparing the organization for future environments. This incremental approach often produces better outcome than attempting the large scale transformations all at once. And the key takeaways and conclusions as we conclude, I would like to highlight four key takeaways from this presentation. From resilience must be approached as a layer strategy, physical infrastructure, intelligent control, and operational governance. Each addresses the different aspects of risk. The second, resilience and cost efficiency should not be viewed as a competing objectives. Throughout the intelligent design and traffic tiering, organizations can achieve the both. Third is operational excellence plays a critical role in resilience. Monitoring, observability, and recovery procedures often determine how effectively organizations respond to the failures. Fourth, resilience should be implemented incrementally. So organizations can achieve significant improvements by following a structured phase roadmap. In closing, the rapid growth of cloud computing, distributed applications, and digital transformations in issues make resilient connectivity more important than ever. Organizations have that invest in layered resilience strategy will become the position to support the business growth, maintain the customer trust, and adapt to future technology demands. Thank you for your time and attention. I appreciate the opportunity to share this research, and I hope the framework provides the practical insights that organization can apply in your own connectivity environments.